OCR A-level physics, nuclear physics 4. And this is going to be all about radioactive decay. And this is the mathematical one, this one. So look at these isotopes of magnesium. So you know what isotopes are. So here's a question. What do they have in common? And then how are they different? Well, what do they have in common? They've got the same chemical properties. Yes. If you put them in acid, then they'd fizz and give off hydrogen. That's what the word isotope means. It means iso, the same, tope, properties. They've all got 12 protons because that's the atomic number of magnesium. So 12 protons. If the atom is neutral, it's got 12 electrons. How are they different? Well, they've got different numbers of neutrons. Yes. If you had a piece of magnesium made with the heavier isotopes, then that piece of magnesium would be heavier. And then there's one more important difference, and that is that those ones there in red, they are stable, and the others are unstable. So these isotopes are unstable, these isotopes are unstable. Now, what does that mean? It means that they are unstable. At some time in the future, they will decay. Okay, there are lots of factors which affect stability. One of them is the number of neutrons. And the ones over here have got too many neutrons. The ones over here haven't got enough neutrons. There are other factors as well, okay, such as surface area and a few other things. But stable and unstable, and the unstable ones at some time will decay. Now, we don't know when they're going to decay. You know, can you predict when you throw a dice? Can you predict when you're going to roll a 6? No. But because radioactive decay is random, it's a bit like throwing a dice. Okay? What we do know is the probability that an isotope will decay in a certain time. And that's called the decay constant. And it has this symbol lambda, and it's measured in seconds to the -1. So the probability that it will decay in a second is lambda, seconds to the -1. But you need to learn that sentence. The decay constant is the probability that a certain isotope will decay in a certain time. Yes? So if we have N, capital N, parent atoms, and then 1 second later, delta N have decayed, yes? Now, the number of atoms that decay every second is called the activity. And it's measured in becquerel, okay? And a becquerel is just 1 decay per second. Okay, so if it's 1,000 becquerel, that means that 1,000 atoms decay in that last second. So the activity will depend on, it'll depend on the decay constant, because the bigger the decay constant, the more probability there is that an atom will decay. And it will depend on the number of parent atoms. It will depend on N. The bigger that N is, the more atoms we have, then the more atoms will decay in the next second. So delta N over delta T equals minus lambda N. Minus because delta N is negative. N is getting smaller. Here's a little question for you to do. You should be able to do this. And the answer is, there you go. So there's a couple of ways that we can model radioactive decay. We can model it using dice, and hopefully you've done this. You get lots and lots of dice, a couple of hundred dice, and then you throw them all, and you take away all the sixes. Now, so the dice that is removed in a throw should be a sixth of N, shouldn't it? But of course it's random, so whether you get exactly a sixth or not is very unlikely. On average, you will get sixth. And the bigger the number of dice that you use, the closer to a sixth it will be. Okay, the larger the number of dice we use, the smoother the curve will be. Yeah, so you start with a large number of dice, you roll them all, take away all the ones that land on a 6, and it'll probably be about 100, won't it? And then you do it again and again and again and again. And you can plot the number of dice against the number of throws, which represents time, and you should get something which looks a bit like an exponential decay. Because it's random, it's very unlikely to be a very smooth curve unless you use a very, very large number of dice. You could also plot delta n against time, and that should also be an exponential decay because delta n is proportional to n. Another way of doing it is an iterative method. We did something like this when we did capacitors. So what we do is we assume that in a certain time, delta t, we assume that the activity is constant. So we can work out delta n, the change in n, just by saying it's minus lambda n times delta t. Yes? For example, let's say n naught, we start with 10,000. And let's say lambda is 0.1 seconds to the minus 1. And then we do it every second. Delta t is 1 second. And we can work out again and again, repeatedly, the value for delta n. And then you take that off n and you do it again. Then you take it off n, then you do it again. And then you plot your graph. And this is a mathematical way, an iterative method to model decay. Okay? Now, the smaller the value of delta t we use, the more accurate our model will be because of this assumption that we're assuming it's constant, yeah, for delta t. Remember again that radioactive decay is random, yes? So in real life, we're not going to get a lovely smooth graph. And then the larger the number of atoms involved, the closer the actual values will be to our mathematical model. So dn dt is minus lambda n, yes? Instead of dn dt, we can write capital A for activity. Try not to get your letters mixed up, but capital A for activity saves a little bit of time, and then we don't need the minus either. Now, the solution to this differential equation gives us n as a function of time, and it is this: n equals n naught e to the minus lambda t. And again, the activity A equals A naught e to the minus lambda t. And both n and the activity falls exponentially, e to the minus lambda t. It's an exponential decay. And if you've revised your capacitors, you know that e to the minus lambda t tells us the fraction remaining after a certain time. Do this. You should be able to do this now. And the answers are in 3, 2, 1. Okay, so the initial number there, well, it's 123 grams. You've got, no, it isn't. It's 2 times 10 to the minus 6 grams, I beg your pardon. But the mass of a mole is 123 grams of sodium. So that's the number of atoms there. So the activity, lambda n, is that, yes, e to the minus. What I've done here is I work out e to the minus lambda t and then just multiply that by the initial activity to get the activity at any time, yes. And then to do the last bit there, you do A-level maths, you can take logs, can't you? So if e to the minus lambda t is 0.1, then e to the lambda t is 10, so log of 10 is lambda t, and then you get t in seconds, change it to hours, 43.8 hours. So to work out the time, you're going to have to take logs, remember that. Now, Gordon, my mate Gordon here, how long will it take the activity of a sample to fall to 50% of its initial value? And that's the half-life, okay? And I've just a little derivation at the top there. The half-life is log 2 over lambda, or lambda is log 2 over the half-life. What is the half-life? The half-life is, so here are some different definitions, the time it takes for the activity to halve, the time it takes for the number of parent atoms to halve, the time in which there is a 50% chance that an atom will decay. So there's some different definitions of the half-life for you. Take your pick. Obviously a very useful quantity. If you know that the half-life is like, 5 seconds, then you know that after a minute or two, there won't be a great deal left. If you know that the half-life is 100 years, then it's still going to be very, very active next year. How do you measure half-life? Well, don't worry too much about the details here, but this is the way that we usually do it. We use something called protactinium-234. Protactinium-234M, don't worry about the M, because it's got a half-life of about 70 seconds. And we can get these things in physics labs called protactinium generators. And basically you've got some uranium which produces your protactinium, and then you shake the bottle and the oil floats to the top, and that's got your protactinium in it, and you can measure the radiation it gives off. It gives off beta minus decay. So you can use a counter and measure the number of counts in 30 seconds, or you can use a rate meter, and that will tell you the activity from the rate meter. So the procedure is, the first thing you've got to do is measure the background count. And then you take that away from all of your other results. You remember that there's lots of little bits of radiation, like radioactive materials all around us giving off radiation. And your background count is usually about 10 counts per minute, depending on where you live. But you need to take that off from all of your count rates. So you shake the bottle and then you let the oil layer float to the top, and that's got your protactinium in it. Measure the count rate every 30 seconds. Yes, so number of counts in 30 seconds for at least 5 minutes. Bit of a typo there. Remember, precautions are all about minimizing exposure. So you can wear gloves, you stay away from it, you keep your substances in locked cupboards with hazard signs on for radioactive material. The only person anywhere near it should know what they're doing. They should be trained to use it, etc., etc. One note is, we're not actually measuring the activity. Why? Because if you imagine all the radiation being produced in that bottle, only a very, very small fraction of that is going to go into your GM tube. What we're measuring is the count rate. Yes, we're measuring a count rate, which will be proportional to the activity. So we can still work out the half-life. But, 90% of this radiation probably won't even leave the tube. And then the stuff that does leave the tube, a very, very small fraction of that will actually go in the GM tube. So how do you get your half-life from the results? There's two ways of doing it. You can plot the count rate against time and do a smooth curve. Yes. And then from the graph, you get the half-life 3 times and take an average. So you could do from 100 to 50, 50 to 25. You can do from 80 to 40. You can do from 60 to 30. But get it 3 times and take an average. A better way of doing it is if you plot the natural log of the count rate against time, then you should get a straight line and the gradient should equal minus lambda. And I want you to figure out why. Remember, I'll give you a clue. Remember about taking logs. Yes. Better because it's better to do a line of best fit than it is to do a smooth curve, especially when your points are all over the place because it's so random. Bit more about carbon dating because it does mention it in the specification. So living things, if something is alive, living things have lots of carbon in them, and some of this carbon is carbon-14, which has a half-life of 5,730 years. Now, when something is alive, we are part of the carbon cycle, and there's carbon coming into our bodies and carbon coming out of our bodies, and the percentage of carbon-14 stays the same while we are alive, But then when we die, the amount of carbon-14 gets less and less because it decays. So if you compare the count rate of the same mass of substance for something which is alive and something which died a long time ago, then there will be less in the stuff that died a long time ago because that carbon-14 has decayed. This method is accurate for samples up to about 50,000 years old, because if it's older than that, then it's the count rate is comparable to background. Okay, and then for things which have only recently died, then obviously it wouldn't be accurate as well. But for things like, things which are about 5,000, 10,000 years old, this is a pretty accurate technique. So here's a little question you might like to have a go at. And the answers are, okay, and hopefully you got that. And, okay, very old piece of cloth now. Calculate the age of the cloth. And it is, there you go.